Let's talk about stoichiometry, which is the study of the amount of matter in a chemical reaction from one chemical entity to another. So as mentioned, stoichiometry is just a way of finding an unknown quantity from a known quantity. And the key link between those two compounds or those two elements is the mole ratio. And the mole ratio is determined from a balanced chemical equation. So in order for us to do stoichiometry correctly, we must start with the balanced chemical equation and then using the mole ratio to convert the moles of our known to the moles of our unknown. And stoichiometry is all based on the law of conservation of matter. Because if we know the amount of the reactant atoms that are present in a reaction, then we also know the amount of product atoms that are present in the reaction. Now, in order for us to study stoichiometries, there must be four assumptions which must be met. The first assumption is that the reaction must be spontaneous. That is, when you put two chemicals, often in solution, together, they will react immediately, right away. These reactions also happen to be fast, so that it happens over the course of minutes, not hours or even days. These reactions are also what's called quantitative. That means they all the reactants will react. There's no impure material that will get in the way. All the chemicals in the reaction will react. And lastly, the reactions are stoichiometric, which means it will always react in the mole to mole ratio as prescribed in the balanced chemical equation. A good way to study stoichiometry is also to look at non-examples. So these are examples where we cannot use stoichiometric principle. For example, the process of rusting, even though it is spontaneous, it is a very slow reaction. It occurs over weeks, months, maybe even years. So we cannot use stoichiometries to study rusting in the everyday world. Another example is combustion of, let's say, wood. And combustion of wood is a mixture of complete combustion and incomplete combustions. So there are different chemical equations happening. Therefore, we don't have one stoichiometric ratio that we can use for the combustion of wood. So therefore, we cannot use combustion of wood as an example of stoichiometry. While there are different types of stoichiometry, the one we're going to focus on right now is what's called gravimetric stoichiometry. In gravimetric stoichiometry, there are mass measurements involved. So in chemistry, we're often using grams or kilograms to measure mass, but in the States, for example, they could use ounces and pounds. But it's really important to convert everything into grams. And the mass here could be determined as either the product or the reactants. If we know one, we can determine the other through the process of stoichiometry. Again, you need to have a balanced chemical reaction in order to do this, and you also need to remember how to convert mass to moles for any particular chemical compound, as well as back to moles from mass. So with that, we can predict the mass of the product from if we know how many the mass of the reactant and vice versa. So let's go over the steps we need to do in a gravimetric stoichiometry example. First, again, we need to write the balanced chemical equation. We also then will list the mass given as well as the molar mass of the compounds involved. Then we need to convert the mass of our measured substance, so our known compound, into moles. Then we'll use our molar ratio to convert from our known into our unknown, or you can say we are from our given into our required compound. And then lastly, we convert the moles of our required or unknown compound into the mass of the required or the unknown compound. We can also represent these steps in a diagram. Here we have the mass or in grams of our given. Sometimes we call that a known compound. And then we need to convert that into moles using the molar mass of that known given compound, and then transfer it to, or exchange it into the moles of our unknown using our molar ratio. And then lastly, we find the mass of our unknown or our required compound, which is, we said, sometimes is also known as a unknown. And to go from moles to grams, once again, we need to use the molar mass. However, it is important to note that these two molar masses refer to different compounds. This is the molar mass of our given or known, and this is the molar mass of our required compound or unknown compound. Let's do our first example. Here we're asked to find how many grams of oxygen is required to burn 10 grams of propane, and propane is C3H8. So first we write our balanced chemical equation. 1 mole of propane reacts with 5 moles of oxygen, yields 3 moles of carbon dioxide and 4 moles of water vapor. Then we convert our mass of propane, which is 10 grams, into moles of propane by dividing by the molar mass of propane, which is 44.11. So then we get 0.227 moles of propane. Now that we have the moles of propane, we can convert it into moles of oxygen using our molar ratio. We go back to our balanced chemical equation. We see that we have 1 mole of propane is combusted with 5 moles of oxygen. So our molar ratio here is 5/1. It will always be your unknown over your known, or your required over your given. And since oxygen is our unknown or required, the 5 goes on top. So we take 0.227 moles of propane, multiplied by 5/1. Our moles of propane get canceled out, leaving us 1.13 moles of oxygen. Then we need to convert the moles of oxygen into the molar mass of oxygen. So 1.13 moles of oxygen multiplied by 32 grams per mole. The units moles cancel out, leaving us 36.3 grams of oxygen. It's important to remember that oxygen here is O2, so the molar mass of oxygen is 2 times 16.00 grams per mole, or 32 grams per mole. Let's try a second example. Here we have 20 grams of butane, and butane is C4H10, is completely burned in a lighter, and how many grams of carbon dioxide gas will we produce? And if you remember, in complete combustion, we get CO2 and water vapor. So the first thing we need to do is to make our balanced chemical equation. We have butane reacting with oxygen to give us carbon dioxide and water. And if you take a moment to balance the chemical equation, you'll find the coefficients is 2 moles of butane, 13 moles of oxygen, 8 moles of carbon dioxide, and 10 moles of water. Then we list all of our given information. We're told we have 20 grams of butane, so we write 20 grams, and we calculate the molar mass of butane to be 58.14 grams per mole, and we're required to find mass of carbon dioxide, so we put our M here, and we calculate the molar mass of carbon dioxide to be 44.01 grams. So now that we have our basic information organized here, we're going to try to solve this question now with one step using what's called unit analysis. We're going to cancel out the units where we can, keeping the proper units where we want, and to get our final answer. So here we're starting with the mass of our butane, 20 grams. And in order to go to the moles of butane, we need to do division by the molar mass, which is 58.14 grams per mole. Now the grams canceled out, leaving you with moles of butane. Then you convert the moles of butane into moles of carbon dioxide by going back to our balanced chemical equation. And the coefficient here is 2 butane to 8 CO2. Our CO2 is what is required, so we put that on top, 8 moles of CO2. Our given is moles of butane, so we put that on the bottom. Now, moles of butane cancels out here, And lastly, we need to go from moles of carbon dioxide to grams of carbon dioxide by multiplying by the molar mass. However, this is the molar mass of the carbon dioxide and not the molar mass of the butane. And then lastly, the units moles of carbon dioxide cancels out, leaving you with grams of carbon dioxide. Lastly, you do your math with your calculator, and you take 20 times 1 divided by 58.14 times 8 divided by 2 times 44.01. You hit enter, and the digits tell you 60.6. Well, and then the units is grams, because that's what we were left with our analysis earlier. So the final answer is that we have 60.6 grams of carbon dioxide is formed when we combust 20 grams of butane. So this unit analysis method takes a little bit of a while to set up, but it is easier to do mathematically because we only need to do one set of calculation. Let's try another example with our unit analysis. So in a reaction of iron 3 hydroxide with carbon monoxide, what mass of iron 3 oxide would be required to produce 100 grams of iron? So the first obstacle to this is to come up with a balanced chemical reaction. So in our question, we note that iron 3 oxide and carbon monoxide are the reactants. So we can write that on the left side of the arrow. Now we have to see that the iron 3 oxide would be is a reactant to produce 100 grams of iron. So iron, we know, must be a product. And what else must be formed? Oh, it must be carbon dioxide, because we still have carbon monoxide, and it takes one of the oxygen from the iron 3 oxide onto itself. In fact, it takes all of the oxygen from iron oxide onto itself. So there is your balanced chemical reaction. Then we list our information. We're asked to find what mass of iron 3 oxide is required. So that is our unknown. And we're told we need to produce 100 grams of iron. We're told that information, so that is our given. So then the last thing we need to do is to determine the molar mass. And the molar mass of iron 3 oxide is 159.7. And the molar mass of iron is 55.85. So now we're ready to set up our one-step math. In order to find the mass of the iron 3 oxide required, we start off with the mass of our iron here. We convert that to the moles of iron by dividing by the molar mass of iron, which is 55.85. Then we go into our mole ratio. It's 1 to 2, because for every 2 moles of our iron, we need to have 1 mole of our unknown. 1 mole of our unknown here is our iron 3 oxide. So then we have the moles. Now we have the moles of the iron 3 oxide. We now need to go and convert the moles of iron oxide into grams by multiplying by the molar mass of iron 3 oxide. And then all the units cancels out except for the grams of iron 3 oxide. And you do the math in your calculator, where you punch in 100 times 1 divided by 55.85 times 1 divided by 2 times 159.70, hit enter, and your answer with sig is 143.0 grams of iron 3 oxide. So regardless of which method you use, if you use 3 steps or you use the one-step unit analysis, you must start with a balanced chemical equation, and then you convert your mass of your given into moles, and then use the mole ratio to convert from moles of your given to your moles of your required, and then finally use the molar mass of your required compound to convert that into the mass of the required compound. One last example here, and this is a little bit more difficult because we're not told of our reactants or of our products. However, we're told we have a reaction between aqueous sodium carbonate, so Na2CO3, aqueous, reacts with aqueous calcium chloride, CaCl2, aqueous, and then mass of calcium carbonate. So that is one of our products. In fact, let us complete the balanced chemical equation first. And this will be a double replacement reaction. Double replacement reaction. So now we're going to get NaCl aqueous plus calcium carbonate. And checking our solubility table, we know that it's going to be our solid. So we can find a mass. And our balance equation is 1, 1, 2, 1. And then we can then list our information, what mass of sodium carbonate, so M equals question mark here, and required to produce 2.5 grams of calcium carbonate. We can also determine the molar mass, and the molar mass of sodium carbonate is 105.99 grams per mole. And the molar mass of calcium carbonate is 100.09 grams per mole. So let's do this in a three-step method. So step one is to convert the mass of sodium carbonate into, of calcium carbonate into moles of calcium carbonate. So we have 2.50 gram. Divide by the molar mass of calcium carbonate, 100.09 grams. And that is going to be 0.02497 moles of calcium carbonate. So that was step one. Step two, we convert the moles of calcium carbonate into moles of sodium carbonate. And our mole ratio here is 1 mole of sodium carbonate, and over 2, also still 1 mole of calcium carbonate. So the mole here was 0.02497 moles of sodium carbonate. And then lastly, which I'll try to squeeze in here, is to multiply that by the molar mass of sodium carbonate, which is 105.99, that's a 5 grams per mole, which then will give you 2.65 grams of sodium carbonate. So this three-step method is a little bit more involved, but it should be a little bit more clear. Whichever method you use, it's up to your personal preference. So I encourage you to try some of the practice questions that you have and ask your teacher any questions that you may result out of that. Good luck.